Thank you. Okay, so good morning, everyone. I'm Alberta Aversa. I'm a PhD student in Politecnico di Torino. And I will present you today the work we've done on laser powder bed fusion of aluminum-based materials. So I will present you a material science point of view of this process. And the process we use is a powder bed process, so it's a different process. So our main goal in this project were to study the mechanical properties of aluminum-based materials, to develop new material and new composite, especially for these technologies, and to study the post-processing heat treatment that are suitable for these samples. So only as an introduction, the most used aluminum alloy in additive manufacturing is the aluminum silicon 10 magnesium alloy, or mainly the aluminum silicon alloy. Why? Because silicon gives a good fluidity in the molten state to the alloy, so the molten pool can spread, and we have a good consolidation. And then also because we can have a small, narrow solidification range, which allows us to have crack-free samples. Here we have the mechanical properties of the aluminum silicon 10 magnesium alloy in different conditions. So we have the yield strength and the UTS. And if we compare these mechanical properties with the mechanical properties of the same alloy made by casting and T6, we can see that we always have higher mechanical properties in all conditions. So this is the real advantage from a material science perspective of the additive manufacturing process. So even this is really a promising thing. If we look at high-strength aluminum alloys, such as the 7075 alloy, we can see that the mechanical properties are higher. And these alloys are, unfortunately, not processable by powder bed additive manufacturing because they strongly crack during the laser scan because of the residual stress and the liquefaction cracking phenomenon. So the goal was to find new material that have higher strength for powder bed additive manufacturing processes. So how to find new materials? So at first we thought about building composite, then to build new, to produce new alloy which are good and can take advantage of the fast cooling that arises during the laser scanning. And then we also focused on the heat treatment, so how to improve the microstructure of this alloy. Then we also were interested on understanding the interaction between the laser and the powder bed. And so we did some single scan tracks analysis, so a single scan, a single laser scan on a powder bed, and we were looking at the shape, the microstructure, and the properties of the single scan. We did this also in order to speed up the development of new materials. So we can, instead of buying kilos of powders and have a whole job, in order to see how the material behaves under the laser, we just do a short single scan with a few grams, and we can have an idea of what is going on in the process. So only a few words about the machine we use. So all the samples you will see in this presentation were built with this machine. It's an EOS M270 synth system. The main characteristics are there, where the most important is the laser power, which is up to 200 watts, and the building platform temperature, which can reach 100 degrees C. This is the scanning strategy we use. So we have some scan, and then every layer, the scan direction rotates of 67 degrees. In most of the presentation, we will use the volumetric energy density. It's a parameter that gives an idea of which is the energy input that we give to a scan. So it's power divided by scan speed and some parameters. And it can only give an idea of what's going on. So why to produce composite by additive manufacturing? So composite have a lot of advantage from a mechanical point of view. So they have high stiffness, high strength, low CTE, and etc. But when we produce composite with conventional production technologies, we have to, there are many problems related to the wettability of the particles. So the particles do not wet and do not disperse homogeneously in the part. And also they can agglomerate, and the composite have also difficult post-processing. So it would be really interesting to produce composite with an homogeneous dispersion, because the layer by layer process allows us a good dispersion of the particles. and that in a near-net shape component, so we can reduce the post-processing steps. So this was the idea. And so we thought about producing nanocomposite and microcomposites. So we started simply by mixing powders. We have an aluminum particles here, and all these dots, I don't know if you can see it really fine, are nanoparticles. And here we have these irregular shapes, which are microparticles. We simply mix the powder. We put it in the US machine, and what we obtain is some microstructures such as this one. So in the case of the in both cases, we could obtain, by selecting the suitable parameters, we could obtain dense and crack-free composite. In the nanocomposite, it is not possible to see the particles. In the microcomposite, they seem well homogeneously dispersed and not, for example, agglomerated in the bottom part of the melt pool or whatever. So we went to see the mechanical properties. And what we observed, unfortunately, was that this is the curve of the aluminum silicon 10, so of the matrix, and all the curves below belongs to the composite. So we were wondering what was going on, and what we observed is that there was a correlation with the energy density, so with the parameter we were using to produce dense composite, and so it was not possible to produce dense and composite with high mechanical strength. So we had to change way to increase higher mechanical properties. So finally, it is possible to produce dense and crack-free composite by selecting the good building parameter. However, these composites have lower strength with respect to the matrix. So we moved to alloy. So how to design an alloy composition for additive manufacturing. So we chose mainly two ways. So one was to take an alloy which we already knew which was suitable for additive manufacturing and change it in order to take advantage of the fast cooling that arises during the laser scanning. The other way was to take an alloy which was known to be suitable, to be strong for with conventional production technologies, and try to change it in order to be processable by additive manufacturing. So I will start with the first topic, which is the aluminum silicon nickel alloy. So we started from aluminum silicon 10 magnesium alloy. And from the literature, it's well known that the introduction of transition metal to fast cool aluminum can increase the mechanical properties of the aluminum. As we also wanted to have a fine solidification range, an area solidification range, we wanted to be near to the eutectic. So we have an eutectic likely between aluminum silicon and nickel, which is, has 10% of silicon and 5% of nickel. So we chose a composition which was close to that, eutectic. We checked the melting range, so we have this graph. This is the melting range, which is even smaller than 50 degrees, so it was really suitable for additive. How we produced it, we took aluminum silicon 10, we put some nickel, pure nickel in it. So we have this particle, the gray one are aluminum silicon 10, and the white one, like this one, are nickel. We built samples, and we could obtain dense and crack-free samples. So it was promising. We have the microstructure along the building direction, so we can see the usual microstructure made of melt pools. And on the top, we can see the shape of the melt pool as well. Then we went to see the mechanical properties. So we checked the hardness. We compared it with the hardness of the aluminum silicon 10 in a macro scale, a micro scale, and a nano scale. So in any case, we could achieve higher hardness. So this alloy composition seemed suitable. So here we have the nano hardness of the aluminum silicon 10, and while this one is the aluminum silicon nickel. Okay, so then I will move to the other alloy composition, which is the 775, which we changed in order to be processable by powder bed AM. So, as I said, the pure 775 strongly cracks. So we can find all these cracks along the building direction. And this is mainly due to the large solidification range of the alloy and the low fluidity of the alloy in the molten state. So we started adding silicon, and here we have some silicon more, and here this was the composition that allowed us to have a crack-free samples. So we built these samples with some parameters, and if we check the mechanical properties, it was interesting to find that we could achieve higher mechanical properties than the aluminum silicon 10 magnesium alloy. So here we have the curve of the C modified 7075, and that one. So we could reach 315 as UTS, as EL strength, and 387 as UTS. Then we thought, why not to perform a heat treatment on this alloy? So we can consider that because of the fast cooling that arises during the laser scanning, the samples are in a supersaturated solid solution. So we can do a direct aging, so age the part and allow to the alloy element to precipitate in the sample. So we could see that the hardness increases. And we selected 2 of this heat treatment, and we could achieve 10% increase in the tensile properties. So as this heat treatment was promising, we applied the same idea to an A357 alloy. So this is an alloy very similar to the aluminum silicon 10. It contains 7% of silicon. And so we did the same thing. We built the alloy. We checked the hardness. It increases with the time. And so we did this heat treatment on tensile sample, and we could also achieve an increase of mechanical properties. So the blue and the green curves are the aged one. So if we compare these mechanical properties with the mechanical properties of an A357 sample built by powder bed AM, but with the classical T6 heat treatment, so solution, quenching, and aging, we can see that our direct aging can achieve higher mechanical properties. So as a conclusion about new alloys, we can say that the introduction of transition metal to fast cool aluminum is really promising, that the silicon can reduce the cracking, can avoid the cracking of the 7075 alloy, and that as built sample can be considered as a supersaturated solid solution, and so a direct aging treatment can allow the precipitation of the alloying element, and so the strengthening of the component. So then I will move, as I said, to the single scan track analysis. So we did some single scan tracks. So the scan was just doing a line on a powder bed. And we chose 3 aluminum-based materials. So we have the classical aluminum silicon 10 magnesium. We have the A357, which contains lower silicon content. So instead of 10, 7% of nickel, silicon. And the composite, which contains 1% nano titanium diboride particles. So the main difference between these 3 powders are that these powder, which contain less silicon, is less fluid in the molten state, obviously, and it has also a lower laser absorption, probably, because the silicon is probably responsible for most of the laser absorption in aluminum silicon alloy. So it is less fluid and has less laser absorption, while the titanium diboride is a particle which absorbs most of the laser. So how we did this single scan track? This is the inside of our machine. We built a modified building platform. So we had this platform, which was made of aluminum magnesium alloy. So we had to build some discs made of the same material, or at least a material which was similar, in order to have similar properties, such as the thermal conductivity and everything. So we did this discs, which are aluminum silicon 10. We put it in the machine, and we had also to find a way to tell to the machine to design only a single scan. The US system is quite close, so it wants to do a contour, to draw a contour of the part, and the contour, which is the black curve here, is done with fixed parameters, so we couldn't change it. So we said to the machine to build a larger part with some lines very far from each other. So the red lines that we will see inside are the lines that belongs to the single scan tracks. So when we analyzed this scan, we could find that mainly 5 morphologies, which are not enough lead. So in this case, the power was not enough to melt the scan. we could see balling. So in this case, the scan breaks because of surface tension effect in separate drops. Then we have a thin and stable scan. So it seems promising. Here we have also the cross sections. So here as well, the depth of the scan is quite similar to the height of the scan, so the growth. Then if we increase the energy density, we go to irregular scan. So in this case, this is a different irregularity with respect to that one. So we can see that the scan is not broken, but it is strongly asymmetrical. And then we go to two thick scan, which are very large and very deep as well. So this is the most promising scan. While this one, even if it is stable, it is not promising. It will waste a lot of power. It will probably dirty the machine, change the composition, and will have a lot of negative effects. So if we look at the scans plotted with respect to power and scan speed, we can see how they, so the colors are based on the stability zone. So we have here thin and stable, not enough lead, balling, and etc. So we can draw these maps, which are processing maps. We can simplify these maps with points. So we have power and scan speed and all the stability areas. So what we've done was to compare the process windows of different materials. So we have aluminium silicon 10, and the green area is highlighted, which is the thin and stable area. Then 8357 and Nano titanium right, the composite. So it is interesting to note that the 8357 alloy has a really narrow processability window. So this is probably due to the lower fluidity and the lower laser absorption. While Nano titanium diboride has process windows which moves to higher power, and so higher scan speed, sorry. And as you can see here, the blue dots, which are the two thick lines, are 4 instead of 2. So this indicates that there is a higher laser absorption. So then what we did, we cut the single scan, all single scan. This is an example. We have the cast area, the single scan, and we measured all these geometrical features. So we have some interesting trends that can explain which are the phenomena that take place. The last thing we've done was to perform some nano indentation analysis on this single scan track. So we can see here is the cast part. Some really red, strong, hard part are the precipitate in the cast part, while the green area is in this case, is the single scan track. And what we wanted to do was to see the effect of the building parameters, so only of power and scan speed, on the nano mechanical properties of the single scan tracks. And so we could find some interesting correlation between parameters and nano hardness. So as a conclusion, this method, so the single scan track, can speed up the development of new materials for powder bed AM. And with this study, we could find a correlation between building parameters and scan track quality, stability. And we observed also that the feasibility window, so the process window, strongly depends on the powder properties. So thank you. I would like to thank Diego Manfredi and all the researchers from the Istituto Italiano di Tecnologia, IIT, which is an institute with which we collaborate, and some PhD students and master students of our group, and all AMAZE project partners. Thank you.